Okay, hello everybody. Welcome back to Organic Chemistry. This is Friday. I'm rocking the the Hawaiian shirt today. So anyway, so things that are due this week. The homework for section 2.1 is due today. The section 2.2 will be due next week. Section 3 is going to be moved as well. So don't worry about that. So just worry about getting that module 2 homework, not the module 2.2 homework done. We should finish up all of 2 today and start 2.2 today in the lecture. Okay. And then we should be easily caught up. We're a little delayed. We should be easily caught up by the end of next week. Also on there is, let's see. So on Canvas, I have uploaded the newest slides, the 2.2 slides, and the 3 slides should also be uploaded to both Top Hat and to Canvas. I'm double checking that. I'm almost positive they're there, but I'm going to look at that files. And Module 2 and Module 2.2 are up. Module 3 is not up yet. I'll have Module 3 up tomorrow. Well, sometime today. So module 3 is going to be acids and bases. Okay. Let's see. All right. Okay. So that is all the administration I have. Does anybody have any questions before we begin the lecture? Okay. So what I'm going to go ahead and do is share my screen right here. Again, there's the group chat here is open, so you can make comments there, or you can raise your hand on the participants. I have that set up as well. And then I have the thumbnails over on the side here. Okay, so we're going to continue on. And remember, what we're going to be doing is labeling all of our functional groups. We need to be familiar with all of our functional groups, and then where they are on that priority scale, familiarity with the priority scale. Now, in this basic, in this first blush right here, what we're going to do is that the group we're talking about is the priority group, and therefore it is what the compound will be named for. Okay, so this group of compounds all involve the carbonyl, which is a carbon-oxygen double bond, and we have a really wide variety of functional groups available to us here. We have everything from the simplest aldehyde, which is just 1 carbon bonded and 1 hydrogen bonded, up to many more different kinds of atoms and what we call heteroatoms, which are atoms other than carbon are going to be bonded to this carbonyl compound. So the first set here is, okay, let me get, there we go, is the aldehydes and the ketones, okay? So in the aldehyde and ketone, the big difference between the two is the aldehyde has a hydrogen bonded to the carbonyl, and the ketone has 2 carbons bonded to the carbonyl, okay? So there is actually a simple aldehyde here that has 2 hydrogens here, and it is called formaldehyde. However, all the other ones will follow these rules, okay? So let's look at the rules that we have. Come on, there we go. Okay, so if aldehyde is the highest order functional group in our system, we name the compound for it. Okay, so one of the lower ones we had was the alcohol, but the aldehydes are above it. And so the way we denote that we have an aldehyde in our system is, and sometimes you might want to just draw that hydrogen there to make sure you remember it's there, is you start with the, drop the E at the end, which means it's a hydrocarbon, and you add the Al. So if it was just the aldehyde of ethanol, or ethane, it would be ethanal. So we just drop the E and add Al. That's the indicative of the aldehyde. And so it's easy to remember aldehyde, al. So it's easy to do. And we follow all the other rules. We find the parent chain, which is the longest number, including that functional group. And we try to give the aldehyde the lowest number possible. Now, because there's a hydrogen bonded here, it's typically in the number 1 position. Okay, so you typically have that aldehyde in a number 1 position. Okay, and so you would follow all your other rules where your aldehyde is your number 1 position right here, and then we number the longest thing possible, and then we add all of our all of our substituents. So in this case here, we have an ethyl group on this 3 carbon, and we have a OH group on our 4 carbon. When an OH is naming the compound, we call that all, or an alcohol, right? In the case that it's a substituent, we actually call it the hydroxy group, okay? So we will, of course, take our substituents and put them in alphabetical order. So you end up with the 3-ethyl, 4-hydroxyl, hexanal. So that al at the end tells us we have the aldehyde. So what if we don't have an aldehyde? What if we have a ketone? And the big structural differences of the ketone is we have 2 carbons bonded to that carbonyl. And because of that, it has different properties, and we have to name it something different. So in the case of having a ketone, we drop the E at the end and add ONE to denote that it's the ketone, okay? So again, it's easy to remember because "one" is within the name ketone, and we put that at the end of the word. Now, we do the same thing where we try to put the ketone at the lowest number possible, but it can never be at number 1 because you have 2 carbons bonded to that carbonyl. So it's very common for your ketone to be at least 2 or higher, okay? So what we'll do is we will take our name and start and get the longest chain containing the ketone carbon right here, and we'll start numbering from that way. And then we do what we do with all of our other nomenclature, where we put, we number the chain, we number where our functional groups are. This is a functional group, so we have to have our 4-ene somewhere in our answer. And here's a functional group. We have to have a 3-bromo somewhere in our answer. Okay, so let's see. The ene is telling us the nature of the carbon, which means it's an infix. So we have to put it right after the number of carbons in the parent chain. We have a total of 5 carbons in our parent chain, so that's penta right there. And so our name becomes 3-bromo pent-4-ene-2-one. Where did the 2 come from? The 2 comes from where the carbon is on the ketone. Notice on the aldehyde, we didn't put the 1, okay? Because it's typically at the end of the chain and 1 is understood. But with the ketones, we typically add the exact location. So for example, if we had a simpler one like this, this has a common name called acetone, but this is actually called 2-propanone. Propane. Propone. Ah, sorry, let me erase that and try again. I have the wrong stylus and it's a much different feel to it. Okay, 2. There's 3 carbons, so it's prop. It's on the 2 position. Propone. There we go. So again, it's the longest chain. Locate where your ketone is. Okay, so the next functional group we're going to talk about is the carboxylic acids. Okay, the carboxylic acids have the highest priority of any other functional group. And so if there's a carboxylic acid anywhere on your chain, it's going to be named for that. And so because of that, they have so many different functionality groups to them, we actually are going to start with the carboxylic acids and name all of the different derivatives of carboxylic acids from that. So just like we did before, we're going to drop the E at the end of the hydrocarbon name, and we're going to add oic acid. Oic acid. Okay, so that's telling you you have a carboxylic acid. It's an oic acid at the end. And again, we always number from the carbonyl carbon of your carboxylic acid and number through the rest of your chains. So in this case here, since this is our carboxylic acid right here, we're going to start with 1, get to the end of our chain. In this case, we have 6. So we have to say that we have 6 carbons. If we did not have that triple bond there, it would be hexanoic acid. Okay, but because we have that double bond in here, that triple bond in here, we have to demonstrate where that infix is, where that nature of that triple bond is, and that happens to start at our 2 carbon. So we have to go 2-il is for our triple bond. Our only other substituent here is our bromine on this 5 position, so that's going to be 5-bromo. 5-bromo, and we have 6 chains, so that's where our hex comes in. So if we add all our components together, we have 5-bromo hex dash 2 dash YN for that triple bond, and then oic acid. Oic acid. Oh, I do not like this stylus. Can't find my other one. Okay. All right. So that's the first carboxylic acid derivative. And again, carboxylic acid, highest priority, always starts with that number 1. Okay. So the first derivative we're going to talk about from that is where we take the hydrogen off that carboxylic acid and we add another alkyl group. Okay. So typically they're made where we take an alcohol and a carboxylic acid and combine them together. But the idea here is that you now have a carbon bonded to that carboxylic acid oxygen, and so it's an alkyl group. So when we name these, what we name them for is if we have whatever the chain is here, if we have 4 carbons, it'd be the butyl group, and then we have a space, and then we say whatever the hydrocarbon was for this one, however long this chain is, and then we say O8. At the end, O8 signifies that you have an ester, but you have to have the one side of the ester a space, then name the carboxylic acid and put O8 on it. So let's do one of those right here. So we have to name the 2 sides separately. So the first thing we have to do is identify where our carboxylic acid is. And our carboxylic acid would have been on this side here, and it would have had a hydrogen bonded to the oxygen here. But we've turned it into the ester, so we now have to name the carboxylic acid first, okay? So our carboxylic acid has a total of 4 carbons, which makes it butane, butane, right here. But because it's a carboxylic acid, we drop the E and add O-A-T-E because we have an ester. So it's butanoate, butanoate, okay? Now we look at how many carbons are on the other chain attached to the carbon, attached to this oxygen. We don't count the oxygen, only the carbons attached to that oxygen. We have a total of 2, and that would be the ethane or the ethyl group. So we have ethyl space butanoate, okay? There we go. So this again, we want to get very familiar with all these different functional groups in this chapter because we're going to be using them throughout the rest of the chapters. In fact, we'll be using them in the spectroscopy chapter as well. Okay, another derivative of carboxylic acid is where we take that OH off of the carboxylic acid and we add an amine, okay? So this changes it from amine with, if it had just a carbon bonded to it. If it has a carbonyl bonded to it, we call it the amide, okay? And so when we do that, what we do is we name the longest chain that contains the carboxylic acid parent, and then we add the word amide to the end. Okay, would this be valid if the other side had more carbons as well?
Yes. That was for the previous question.
Yes.
By the way, yeah.
That's a great question. Okay. All right. The question is, what if this side right here had more carbons than this side here? Okay, great question. And the answer is always name it for the carboxylic acid first. So the carboxylic acid is always the base. And then whatever the group over here is. So if we put, this group here, so this would be the ethyl hexyl group, it would still be ethyl hexyl butanoate. Okay. The carboxylic acid is always named first, and then the chain is always in the front as a substituent. Okay? Answer your question? Good question. I forgot about that. Okay. So now we're moving to the amide, which is another carboxylic acid derivative, and we do the same thing. We name it for where the carboxylic acid was first. So if we look right here, this is where the carboxylic acid would amine, which means we number from that carbonyl of the carboxylic acid out that chain right here. And so all the other rules apply. We have our a double bond here, so we need to do the En, and we need to show where that is. We have a total of 5 carbons, so we have penta. We have a substituent here, so that would be the 4-hydroxy. And if you look at this, we have our 2 carbons coming off our double bond are opposite each other, so that's trans. So that gives us our trans, our 4-hydroxy, because it's the 4th carbon over from our carbonyl, penta, 2-ene, and then we just add the word amide to the end. Notice there's no space, because the amide signifies that you had a carboxylic acid that you derivatized with this nitrogen. Okay. Now, amides have another possibility to them. Okay. And the other possibility is that you can have things bonded to the nitrogen just like you have it bonded to the oxygen in esters. And we have to figure out where that substituent goes in our name. Okay. And as it turns out, we can't just have a number, because we don't number the nitrogens, we only number the carbons. So we have to signify that there's a group on that nitrogen by putting the letter N. That indicates that it's attached to the nitrogen in the system. Okay, so in this example here, we're going to have to name for the carboxylic acid first. So we, in our minds, cut it here. We count up to the highest number of carbons, which in this case is 6, but we still have a substituent, and that's going to be our 3-ethyl substituent. Okay, it's in the 3 position and it has 2 carbons. And then we have another carbon bonded to this nitrogen. Okay, so the nitrogen just tells us we have an amide. This methyl group here we have to locate, and we locate it on the nitrogen by putting the letter N. So we have our substituent at 3-ethyl -N-methyl, and then we have 6 carbons on our chain, hexanoic acid, but we chop off the oic acid and add amide because we have that nitrogen bonded there. Okay. And just like all other substituents, we alphabetize based on the alkyl group. So what if you have 2 on there? Well, you have to name both of those. If they're the same group, you can do something like dimethyl. If you have 2 different groups, you have to signify the 2 different groups and show that they're both on nitrogen. So if we break our carbon here, and let's name our carboxylic acid first, 1, 2, 3, 4, 5, 6. So it'd be hexanoic acid, but oh wait, we have a triple bond. We have to make sure we add our infix, and it's on the 3 carbon, so it's going to be 3-ene, because it's a triple bond, 3-ene, right there. We have 6, so we have a hexa somewhere. Actually, we're dropping the A because we have the eel. We dropped the A right there. And let's see, we have a substituent here on the 5 carbon. Ooh, but we have another methyl group here, but it's on the nitrogen. So this one's going to be a 5-methyl, and this is going to be an N-methyl. Okay. oh, what if the alkyl group on the nitrogen branches? Then you have to name it as a bracketed branched hydrocarbon with an N on the outside of the bracket. Good question. I probably won't do that though, but we'll continue. Okay, so this is going to be an N-methyl over here. However, whenever we have multiple substituents of the same name, we group them together and say di. So how can we make sure we have di and know that it's on the 5 and the nitrogen? Well, we say dash N for the nitrogen, comma 5. Notice the N comes first because otherwise we would do them number-wise. However, the letter N does not count as a number, so we put it first and then the number second. So we have an ethyl group on the nitrogen, so that'd be N-ethyl, N-methyl, 5-methyl. So ethyl comes before methyl alphabetically. So our final name is going to be N-ethyl for this group right here, N5-dimethyl for this methyl and that methyl, hex for the 6 carbons, 3-ine for the triple bond, and amide because it's a carboxylic acid. Okay. Okay. Are you starting to see the pattern and how to break these things apart and put all the different segments together and then follow all the numbering rules and alphabetization rules to get to grow everything? You know, it's better to use the system, draw all the different components out, and then kind of piece them together in the right order. That way you don't forget a functional group or a substituent. Okay, so another derivative of the carboxylic acid is instead of having an alkyl group on it, you have another carboxylic acid. And so what you've done is you've taken 2 carboxylic acids and removed water to bind those 2 carboxylic acids together. Because we've removed water, we call that an anhydride, meaning that it's removed water, okay? So the way we signify that is if they are symmetrical, meaning that it's the same on both sides, we just name the one carboxylic acid that makes up both sides of the thing and add the word anhydride. So we have propionic anhydride, okay? If they are unsymmetrical, you actually put them in alphabetical order by identifying each side separately and then put them in alphabetical order. So notice they're both carboxylic acids, so I'm going to blow this up. We have the one side is propionic, which is 1, 2, 3, propane, drop the E, oic acid, so it's propionic acid. This was pentane. We drop the E, add oic acid, so it's pentanoic acid. But we made an anhydride out of them. So we have to say pentanoic, space, propanoic, space, anhydride. So you've named each of the carboxylic acids separately, and you know exactly where your system is. Okay. All right, one more acid chloride derivative. And in this acid chloride derivative, I'm sorry, in this carboxylic acid derivative, we've removed that OH and added a halogen, okay? Typically, it's going to be chloride, but sometimes it's bromide. Rarely do you see fluoride or iodine. So what we call these is we call them acyl halides, okay? I'm drawing attention to the acyl. Acyl means that you had a carbonyl that you have a halogen on. So it's acyl halide. And we're going to use that acyl term in a couple other places. Okay. So when we're naming a base compound, like we have ethanoic acid, like this, and we converted it to an acid, to an acyl chloride, we would end up dropping the oic acid and add oil hydride, halide, whatever it is. You would actually show that it's the chloride or the bromide. You'd have to say whatever the halogen is. So in this case here, we have 1, 2, 3, 4 carbons. So that would be butanoic acid. Okay, so if we converted it to the halide, it would be butanol, U-O-eel bromide, right here. But we have a double bond, so we have to use our infix of ene, and it starts on the 2 carbons, so it's going to be our 2-ene. And we see that both of the substituents on our double bond are on the same side, so that makes it cis. Okay, so we're going to have cis but 2e oil bromide. Okay, break it down, put them all together, and don't forget to alphabetize. Okay, so our next functional group we're going to talk about is amines. Okay, amines are similar to amides, except we do not have that carbonyl carbon. All we have is a regular carbon, either an sp3 or sp2 hybridized carbon. And we classify our amines by how many bonds to carbon they have, okay? So in this case here, if we only have 1 bond to carbon, we call those primary amines. 2 bonds to carbon, secondary amines, and 3 bonds to carbon, tertiary amines. Okay. What if the alkyl group on the nitrogen branches? Oh, that was on the other question, right? Yes. Okay, so we have 2 methods to name amines, okay? And so let's go into the first one. The first one is if they are simple and have simple alkyl groups, we just name them for the alkyl group. For example, this is 2 carbons here, so that would be the ethyl group, and we just put the word amine after it, okay? So it would be ethylamine. And if it's symmetrical, you could say diethylamine or triethylamine. Okay, you can just add those there. If they are not symmetrical, you have to name each of the alkyl groups in alphabetical order. Okay, just like we always do. So in this case, it would be ethyl, ethyl, methyl, amine. And in this case, we have 2 ethyl groups, so it's diethyl with the last one methylamine. Okay, so you just name each of the alkyl groups, and if you have multiples, use di or tri, and you add the word amine. The other way to name it is as the substituent on a longer chain. Okay. So in the case of having a more complex alkyl group, we would name the alkyl group and then tack the name amine at the end, but we have to show which carbon the amine's on. So if we were to name just the alkyl group up here first, we have 1, 2, 3, 4, 5 carbons. So we're going to have a penta somewhere, pent, right here. We have a triple bond, so we have to say that we have that triple bond is the 4-ene right here. We have our amine, and it's on the 2, so it's 2-amine right here. And we have 1 methyl group, so we have 3-methyl. Okay, so let's put that all together. We have 3-methyl, methyl, penta, 4-eel, 2-amine. Okay. Okay. So, and we can follow all those same rules to name more complex systems. And just like we did with the amides, where we said that the other alkyl substituents were bonded to that nitrogen, we'll name the most complex hydrocarbon chain first and show that that's where the amine is. And then we can use the end designation to say, oh, we have an N-ethyl somewhere and we have an N-methyl somewhere. And so we'll end up just adding all the different components. Our chloride is on 6. Our alkene is on 6. Total of 8. We have octa. And we denote where our other groups are with the nitrogen. If it's on the nitrogen, it has an N in front of it. Questions on that? Okay. Now, another carboxylic acid derivative we have is what we call a nitrile. Okay. And the reason it's a carboxylic acid derivative is if you took your amide and removed water, you end up with a carbon-nitrogen triple bond. That carbon-nitrogen triple bond is what we call a nitrile. Okay. And because it's that carboxylic acid derivative, it's one of the higher ones. And we go through the same process of break it down. The carbon where the nitrogen is, the carbon that is triple bonded to the nitrogen begins our chain. Because nitrile is the name of the chain, we always begin at that location. And we number our longest chain, of course. And this one, we have an infix of ine, and it's on the 5 carbon. So we know we're going to have a 5-ine somewhere. Okay. We have a total of 6 carbons, so we're going to have a hex somewhere. We have 1, 2 methyl substituents, so we're going to have a dimethyl somewhere. Dimethyl, and it's on the 2 and the 4 carbon. We have a bromo, okay? So let's hook it all together. Bromo comes before methyl, so we're going to do 3 bromo. The 2,4 dimethyl hex. Because there's a 5, we have to denote where that is. 5-eel. 5, I'm sorry, not eel. Ene, and then add nitrile. Notice there still is an E there, okay? And that's to separate, to showing that you have a hydrocarbon other than the nitrile. So there is an E here, and then nitrile. Okay, are you seeing the pattern? We follow the pattern every time and we'll get to a good answer. We just need to make sure we remember what our functional groups are. Okay, so this technically isn't what we would call a separate functional group, but it is such a common side chain on a lot of materials that we actually have a special name for it. And it's this group right here that is this carbonyl with a methyl group on it, right here. Okay, and the most simplest version of that is what we call acetic acid or vinegar, and it is used in a lot of different ways. That acetyl functionality just means that methyl group and that carbonyl. So start looking for that functionality when you see the word acetyl right there. Okay, so its simplest form is acetic acid, which the IUPAC name form would actually be ethanoic acid because you have 2 carbons. So it'd be ethane, drop the E, oic acid, ethanoic acid. And this is a common abbreviation. As we move forward, you might see that as an abbreviation in a lot of different reactions. So it would behoove you to remember that one. If we derivatize it as an amide, we call it acid amide or ethanamide if we were naming it for the IUPAC name. And this is the common name here. This is actually used as a solvent a lot of times, so we'll see that a lot as well. If we have the aldehyde version of it, we call it acid aldehyde. The ketone version of it, acetone. The ester of it, methyl acetate. And the anhydride would be acetic anhydride. So this acetyl functional group is very common, and it'd be something that we'll use again and again and again. In fact, if we had this as a halide down here, we would call it that if we had a chlorine here, we call that acetyl chloride. Okay, so that's if you had one functional group telling you what the name of the compound was. What if you have 2 of the same group that name the compound? Well, we would do that just the way we would do with multiple substituents. We add the word di in front of the suffix. Okay, so if we had an alcohol, our suffix is -all, we would just say diol. If we had an amine, we would say diamine. If we had a carboxylic acid, we would say dioic acid. Okay, so if you had 3 alcohols, triol, 4 alcohols, tetraol, all you have to do is add the number you have. Now this works specifically when you have that functional group naming the parent chain. Okay, now this brings all of our rules together. Okay, so now we have to use something else with us. And if you go to the review, let me actually pull up something else, share. Where is it? I have a document. Where is it? Ah, there it is. Adobe Reader. Okay, you should see this table. This table is on Canvas, and it has the highest priority and what you would name each of the things. If it's naming the compound, it's this level here, this column here that says suffix. So if you're naming the compound for it, this is what happens at the end of the word. If you have a higher priority material naming your compound, and you have another functional group, you have these other groups here to call them. So for example, aldehydes and ketones, we call those oxo groups. An amide actually would be amino-oxo in there. If we have a hydroxy on there, if it's named for something higher, we name it hydroxy. So these are the names you would name other things that are less priority than the one you have. So let me go ahead and go back to my slides. Okay, so now we're going to put all those rules together. So we have 3 functional groups here. We have the ketone, we have the alcohol, and we have the aldehyde. Now, we go to the chart and see that the alcohol is below ketone, which is below aldehyde. So since aldehyde is the highest priority of those 3 functional groups, we have to name it for the aldehyde. So that tells us exactly which side of the chain to number from, okay? So if we're naming it for the aldehyde, we're gonna start on that aldehyde side here, and we're gonna number all the way over to the other side, okay? Now let's locate all of our other functional sections here. So we're gonna have a 3-hydroxy, because it's not an alcohol, because it's a substituent, so it's hydroxy. Hydroxy. We have a ketone on this 5. Now, if we were naming it for the ketone, we have ONE at the end, but because it's not the primary, we have to name it oxo. And so we're going to name it oxo, and the number we're going to use is the number on the carbon that we have here. So we're going to have 5 oxo somewhere in the system. Oh, and we have a double bond, so we have to have an ene in there somewhere. And it starts on the 3rd carbon. So we're going to do 3 ene somewhere in the name. And whenever we have a di-substituted or a tri-substituted, we have to do the stereochemistry of our double bond. And they're on opposite sides, so that gives us oh no, we have 3 things now. So we have to use E and Z, okay? So if we look at this side of the molecule, we have a hydrogen. So that means in assigning E and Z around this bond here, this is our highest priority on this side because we have carbon and we have hydrogen. So we know what side that is. We have a carbon and an oxygen. Oxygen has a higher atomic number, therefore it is This is the highest priority on this side of the double bond. So now we have two things on the same side of the double bond. So they're on the same side, so that makes them Z. Okay, so now we have a Z configuration. We have our oxo named, we have our hydroxy named, we have our double bond named, we have our aldehyde at the end. Let's pull it all together. And so Z, and we put that in brackets out front, 3-hydroxy, 5-oxo. Notice the hydroxy comes first because of alphabetical order. Oxo, hex for 6 carbons, 3-ene because the alkene is on the 3 carbon here, al because of the aldehyde. Okay, so now following these rules, following the priority table, you should be able to name any and all organic compounds with some practice. Okay, questions on that? Okay, our activity that we're going to do next week, we're going to go through all of these rules. We're going to apply them all and practice, practice, practice. But once you get used to, the idea of breaking it up into the different components, alphabetizing the components, you can name any compound we're going to do in class this year. Okay, if there are no questions, I want to take these last 10 minutes and start with section 2.2 IR spectroscopy. And we're going to start with, with the general concept of what IR spectroscopy is, and then we'll start doing actual individual functional groups later. Probably we'll finish that on Monday. Excuse me. Okay. So, as you might know, light is a form of electromagnetic energy. Okay, and so it has an electric component and it has a magnetic component. And it has, and because it has this electric component and this magnetic component, it can interact with matter, especially things with polar bonds. The more polar the bond, the more likely it is for that field to react with those materials. Okay, so the electromagnetic spectrum goes from very high frequencies to very low frequencies. Okay, and in this case, our low frequencies are on this right side here, the radio waves. Literally, you can have waves that have 2-kilometer wavelengths, where the bottom of one wave, it's 2 kilometers before it reaches that point again. Okay, and so those are very long radio waves. And then as we move further closer to what we see as visible, we get shorter and shorter wavelengths. We get to what we call microwave, and so think about your gigahertz areas. Those are, where your microwaves are. Then we get into what we call infrared. And infrared means below red on the visible spectrum. And that's where we're going to be doing our spectroscopy in this particular section here. And then we hit the visible section, which is where we can perceive light. And then we have UV that's just above that, and then X-rays and gamma rays. And then we start really doing a lot of ionizing radiation above that. Okay. So the most important thing for us is IR in this infrared area here. Now, the most common type of instrument we do is what we call an FTIR, which is a Fourier transform. Okay, what that means is it actually can take multiple spectrums in a time domain and then reconstruct it as an absorption spectrum that we see. Okay, I'm not going to make you do that. I just want you to know that most of the time we have, we don't just take one little beam of light going through the sample. We actually hit it with the thing like 64 times, and then it averages all those signals out, and then takes it out of the time domain and turns it into our energy and our intensity domains that we see. Okay, and many of you might have used this. This is one of the coolest things. This is what we call a diamond ATR, which is attenuated total reflectance. Basically, you can just put anything on that, clamp it down, it shoots IR through the diamond, and you get your spectrum. You don't have to prep any more than that. They're really cool. Okay, so I said that radiation, that magnetic and electric component of light interacts with matter, specifically things with polarized bonds. Okay, so we're looking for things with at least a bond that can be polarized or is already polarized. But the first most important thing we have to think about is the frequency at which something absorbs that energy. You have to match that energy to be able to absorb, that bond has to be able to absorb that energy to vibrate more or less. So to absorb that light, it has to be able to absorb it. Okay, there's two factors that control this. Number one, the strength of the bond, okay? The stronger the bond you have, the more it's gonna vibrate. So it's gonna vibrate at a higher frequency. The weaker the bond, the lower the frequency it's gonna vibrate, okay? The other thing that's important is what we call the reduced mass. And the reduced mass is basically the difference in mass between those two atoms. So if you have a heavy atom and a light atom, that's gonna vibrate more at a higher frequency than two atoms of the same molecular weight, okay? And so we'll see this in this table below. Okay, so the thing I want you to draw attention to is that we have our carbon-hydrogen bond. So carbon's 12, hydrogen's 1, and we have a very high frequency of vibration of about 3,000 wave numbers. Notice this right here, this is reciprocal centimeters. The simpler way to say that is wave numbers. Okay, so that's per centimeter. So there's 3,000 waves per centimeter. Okay, just by changing the mass of the hydrogen from hydrogen to deuterium, that isotope with one neutron in it, it changes the mass from 1 to 2, and we see a drop in frequency. Just that change in mass of one neutron can change the frequency that it absorbs at. And then by the time we get to 2 carbon atoms together, the frequency drops again. So that's a demonstration that our mass change controls our vibration. Now let's look at bond strength. If we look at a carbon-carbon single bond, it vibrates at 1200, okay? So that is, you know, a good starting point. It just, they're 2 atoms of the same mass vibrate that. By adding a double bond, that's making it a stronger bond. So it vibrates at a higher frequency. And if we make it a triple bond, that makes it higher again to a higher frequency. So this is where mass is controlling our frequency. This is where bond strength is controlling our frequency. So what that means is every single band that we look at has something to do with the bond strength and or the mass of the atoms. So we can easily figure out which ones are going to be in which area of our spectrum just based on those 2 components, okay? And even when we have other elements, we follow that same trend. The stronger the bond, the higher the frequency. And so what we'll see is, and this is the same. All right. So the last thing I'm going to talk about today, and then we'll move on to the other one there, is that when these bonds absorb that energy, they have different vibrational modes. What that means is that a bond can absorb energy, and it can, the different types of vibrations it can do will absorb at different energies. So we have a bunch of different types of these where we have a thing called, when you have more than 2 atoms, you can have a thing called symmetrical stretch. That's where both of your attached atoms are moving apart at the same time, okay? If they are out of sync with each other, we have what we call an asymmetric stretch. One's moving out while one's moving in. And so you end up with a different frequency because that has a different amount of energy associated. And then instead of moving just out from each other, they can swing back and forth from each other. And that's called a wag or scissoring. And then we also have what we can call rocking, where the entire molecule can rock symmetrically or out of plane or actually twisting. So there's all these different modes, and all these different modes have different energy associated with it. So what we'll see is most of these kinds of modes tend to be lower energy frequencies and are at the lower energy side of our spectrum. Okay, so I'm going to stop there, and then on Monday we're going to go with the 4 primary zones to look for functional groups in IR. Okay, I'm going to go ahead and stop recording, and you can ask questions.